1990s, computer vision applications with structured outputs in the late 1990s, and the theory of large-scale learning in the 2000s. During the last few years, he has focused on clarifying the relation between learning and reasoning, with increasing attention on the many aspects of causation, such as inference, invariance, reasoning, affordance, and intuition. Leon has pointed out that learning algorithms often capture spurious correlations present in the training data distribution instead of addressing the task of interest. These correlations occur because the data collection process is subject to uncontrolled confounding biases. But suppose that we have access to multiple data sets exemplifying the same concept, but whose distribution exhibit different biases. Can we learn something that is common across all these distributions while ignoring the spurious ways in which they differ? I think that he will be answering that question for us today in a presentation on learning representations using causal invariance. So without further ado, let's welcome him to the stage.
Oh, bad news. Well, thank you very much, Anna. Thank you for giving me a chance to speak here in front of an audience that now I'm very afraid because it's much bigger than what I see here. And I'm going to spend some time trying to motivate what I'm doing by first saying that I don't believe what's written in the papers about AI. That you read in the papers that AI is at the corner of the road and everything, and I think we have some serious difficulties that we need to address. And to give an idea, I wanted to show something that you might find amusing. I have a 30-year-old demo here. And so that was written, the numerical code there was written somewhere in '89, and the graphics in '91, '92. So, the data file, I wanted to load it before, but is composed of 480 digits, because this is what we could handle. Actually, no, this is a demo, so we could handle 10 times more. But the demo are just 400. We're going to use 320 for training. That's what I'm doing here. 320 here. And so that's the training set and the testing set. And I'm going to prepare a network. So I'm going to load one. And I'm going to add a few layers because this is too small. The problem of this demo is that it runs too fast. The problem is to make it slower. Okay. It's there. And to make it slower, one trick is to have a lot of graphics. So these are performance plotting. And I can do some more. Some more. And maybe if I go over the training set, I have to initialize my weights and initialize the learning rate. And I can, well, see, it's too fast. So I can slow it down a little bit. Let's see. So you see these digits, they're mouse drawn because we didn't have a camera or a scanner. And that doesn't work. Now we're going to train. So let's stop this and start training. So I'm going to switch off this display of the network, that's too slow. And up, up, and up. Now we're going. So the black thing is the training error. The black dot that you see here is, and the white one is the testing error. So or maybe the opposite, I don't remember. It's going to be easy to see. And this is the error whenever I show an example. Just plotting it, make it almost reasonable. That used to take 15 minutes. I can even go a bit faster, so that because this part of the talk is not going to be. Okay, and stop. Okay. So the point now is that now it works. Yes, I have to do that. It's always harder to do when I'm on a lectern like this. Why? What's going on? So, this is the one I want. Okay, so you see the digits going, and you see that the white thing going up and down means that it learns. And now I can do it a bit slower, so you can know that it works. And yet there are some amusing things you can look. You can look at some specific patterns that are a bit bizarre, like so this one. Well, I know it's a 5. Okay, so I think there is one like this. No, it's been a while. I don't remember the ambiguous pattern by heart. Oh no, it's working really well. Okay, well, it's working. You can add noise, you can do things. So that was 30 years ago. This is a convolutional neural network. It's very small by today's standard. It's trained on 320 examples, which is very small as today's standard. But it learns, it generalizes on a task that's not completely trivial. 30 years with Moore's law. No, the computer speed doubles every year and a half. That's a factor of 1 million. And I told you we could train this at the time on a couple thousand examples. It's not hard to see that the fact that today we can use 1,000 times more examples, 1,000 times bigger networks, is not very surprising. No, it's fundamentally the same kind of phenomenon. It's the same level of things. And what we wanted to do at that time is that, so we knew that this was quite interesting. We knew it was too small, but we knew that would change. And we wanted to find a way to program computers not by programming them, but by teaching them, by training them to do something, like an alternative way to use computers, an alternative way to use, to see how computers work. Instead of being programmed laboriously, detail by detail, we wanted just to train them and make them work in a way that was a little bit more similar to us. It's not AI yet, and there are a lot of other things in AI, but if you can get a computer to do what you want by training it, it's clearly a step. And have we done that? And this is where I'm going to go to my slides, which should be somewhere here. And do what I should have done at the beginning, the title, and my co-authors, Martin, who is a PhD student in New York University, Ishan, he was in Google at the time, and now is in MIT finishing his undergrad. And David, who is a researcher in Facebook, AI research in Paris. And okay, that's an explanation, but the thing is, this is what really puzzled me. That was 2014. Neural networks were back appearing, and we were trying to show some transfer learning properties in vision. And one of the tasks we looked at was the action detection problem in Pascal VOC. And one of the actions is detecting whether somebody is giving a call, is placing a call. And you have images, you have a bounding box, and if the person in the bounding box is calling, is on the phone, we're supposed to say yes, otherwise you're supposed to say, well, maybe this person is doing something else. That looks all very nice, and we get 7% correct. That was the state of the art at that time, and I think it's not far from the state of the art today. But Maxime, who was a PhD student working on this, came back and said, you know, we got 70%, but it really doesn't work. Look at this picture. So there is a row of payphones, which is something that still was there in 2014, and there's a person here. And this person is obviously not calling. But if we move the bounding box in front of the payphone, it's going to say very strongly calling. In fact, whenever there is a person on the phone in proximity, it says calling. So, of course, it's not solving the problem of detecting whether a person is calling. And the worst part of this is that the algorithm is right. If you take the data that you get, typically data you get, pictures you get on the web, when there is a person near a phone, most of the time this person is calling. It's a selection bias. You don't take a picture of somebody who just walks by a phone. When you take a picture of somebody, the phone is calling. So that means that, one, we're not solving the problem, and two, the algorithm is right. So what's missing there? And what's missing there is that you have to realize that the task, detecting if somebody is calling, is a task that we don't know how to solve directly. So we define a proxy problem. The proxy problem is a statistical problem. Here is a data set of yes and no's, and try to replicate that. And between the proxy problem and the task, there is a world of things. Usually we ignore this. We assume we start machine learning by saying, let's suppose we have RID data, and one part is the training set, one part is the testing set. But here you see a practical example where what we want to do, well, we have an RID data set because we split it into training set and testing set. Actually, the Pascal-Vogt people did that. And so it perfectly fits the properties of the machine learning theory, and yet it's totally missing the point. Now, turns out that if you look what's happened in the 30 years ago, we would make the data sets very carefully. Like, for instance, when I was in AT&T Bell Labs, we worked on zip recognition or check amount recognition, or these kind of things. And we'd make data sets that were at most 10,000 or 100,000 examples for the biggest ones. And we would be very careful in curating them so that they represent the thing where we want and everything. And this curation is kind of an art process. And nowadays, as I said, they come from the web. They're in huge quantities. They're not things we can look at. And in fact, the sizes that we want to use are so large that it's impossible for a human to even look at them in a careful way. And they're corrupted by plenty of biases. And if you look at papers, there are plenty of papers that comment about bias. Like this one, the Toralba and Efros, is a computer vision paper where they try to use several object recognition databases and try to recognize a car class in each of them. And basically what they show at that time, that was before CNNs, before the rediscovery of the big results of CNN, what they show is that when you train on one data set, it performs very badly on another one. On the other hand, if you take an image and you want to train a classifier to say from which data set it comes, that works really well. So that tells you that each of these data sets is so specific that it's impossible for the learning algorithm not to catch some specifics of the data set instead of the concept you want to have. So that's something about recommendation system or ad placement systems where you find a lot of causal effects that cause the data to be completely biased. And another one that's quite recent is about visual question answering, which looks like a very nice task. You get a picture, you get a question, and the computer must answer. There's a picture, so what is the color of the tie of the man who is walking in second position? And the question should be red. The answer should be red. So it seems that if you can do this from our biased perspective, it might seem that if a computer can do this, means it understands the image, understands the question. And very quickly, systems get in the 70% correct. At some point, somebody say, hey, stop. There is a problem. If you don't even look at the image, you just look at the question. When the question is, what is covering the ground? The answer is the snow. And when the question is there something on the something? The answer is yes. And that comes back to how the data was collected this first time. Images from the web were captured. And then a first set of mechanical Turkers was supposed to invent questions, and a second set was supposed to give the answers. Now, it turns out that the imagination of people in terms of question is not very big. Like, if they see something with something on the shelf, they're going to say, is there a flower pot on the shelf? Because they saw a flower pot there. But very few are going to ask whether there is a carafe on the shelf or something else while there is a flower pot. It's not natural to ask a question like this. So the result is that the dataset is so biased that the results that were looking very promising were in fact barely better than the ones you can get by just exploiting trivial biases like that. Like look just at the location or just at the image. So the result, what's happening is that the data collection creates a lot of biases. And you have confounding biases, feedback loops in the systems, you have selection biases, and we can control for them. And all our machine learning algorithms absolutely love to take advantage of the spurious correlations. If they can find an easy way to solve the problem, they will use the easy way, not the hard way that requires understanding something. So if I go back to these spurious correlations, what do we say a correlation is spurious? Like I take my phone example. Why do I say that when a person is close to a phone, saying that this is strongly correlated with the person calling is spurious? And the reason is that I do not expect that this is going to work in the future. I do not expect my system is going to be used in situations where I can make this assumption. And the question is, what informs us? Why do we say such things? So we might have substantive knowledge about what this is to give to call. When you call, well, it's not enough to be close to a phone because calling involves interesting consequence that people are going to be informed of something. And you can also ask where does this substantive knowledge come from? And we have to say that whether it's in one person or in mankind, it comes from the past observations. Now, that's the problem, because the past observations, we said, are biased. And this is where there is an interesting concept that you can find in the philosophy literature about causation, coming back to Hume and other people, is that humans are just not looking for correlations, they're looking for stable properties. What does it mean, stable property? It means that you want to see that, let's say, the action of calling is connected to what you see in ways that are stable, that are not going to change. And that means that maybe when we look at the past, we take the data in the past and we say, oh, it's correlated, but the past is not uniform. The past is heterogeneous. Nature doesn't shuffle the data. No, we shuffle the data when we do machine learning. We shuffle the data because we want it to be RID, because this is what we understand. But in fact, when we collect the data, we collect from different points in time, different points in space. Like if you take even the example of calling and take it at different points in time, nowadays it's going to be a cell phone. In the past, it's going to be a big phone with a rotary thing. And if you look in different countries, it might be different too, because people might hold the phone different, they might have different equipment, or in different experimental settings. You can take a high-resolution camera, low-resolution camera. Sometimes I think that when you look at ImageNet and you recognize all these dogs, when you take a picture of a dog, you take a picture with, everybody takes a picture with the same kind of phone, from the same distance, with the same focal length, because this is how you take the picture of a dog. Now, are you recognizing the dog or the subtle noise patterns that tell you how you use your phone and how it was set up? And so then we shuffle the records. We take all this heterogeneous rich data, we mix it, and we say the RID, and we can proceed with machine learning. And that's clearly a loss of information. And so we started to follow a line of work that comes from Jonas Peters in 2016, and maybe a little bit before there was Bruno Meinshausen and Peter Billman in Zurich in 2015. We consider the data set we have doesn't come from a single distribution, but comes from several distributions that we call environments. Initially, first a discrete set, PE. So we have XE, YE for E equal 1, 2, 3, 4, 5, small number. And so we have a bunch of these distributions. And we have training sets that I'm going to assume large for now, provided for some of these distributions. And we want a predictor that's going to work for many of them. And the important point is that I'm not going to assume that some distribution, the ones I have, are kind of random samples of the possible environments. So what I call an environment is one of these distributions. I'm just going to say I have some of them. So when you have a situation like this, the classical way in statistics is to try to be robust. You're going to say, I'm going to minimize the maximum over all environments. So if you look at this formula here, maybe I'm going to use the mouse so that it's visible. You have the minimum over your family of functions, of the maximum over all environments, or let's say the squared error. And you can have an baseline. I'm going to discuss the baseline later. So that says that you want something that's going to perform well on all of them, not just one of them or a mixture of them. And then you realize there's a problem. Suppose you take the calling example. You have two environments. One of them is made of very clean pictures taken last year, and the other one is made of pictures from the 20s, black and white, grainy, not pretty. Well, it's going to be harder. So the error you're going to make on the old pictures is going to be higher because you don't see that nearly as well, even though the fonts were bigger, but that's another detail. So you might say, well, for each of this environment, maybe I want a baseline, and I'm not going to even to say how to compute the baseline. And what I want is that by having a single function for all environments instead of one trend for each environment, I'm not losing too much compared to the baseline. That means that the relative loss of accuracy compared to the baseline is not large, even though I'm going to use the same function to work in all these environments. But when you have this, you can start doing a little bit of mathematics and restate the problem. I say, is the argmin of M such of all E, M is greater than what I want to minimize. And when you have a constraint problem, you can use the Karush-Tucker theory. And basically it tells you there is a set of lambda positive such that the solution of that problem is a first-order stationary point of a proper mixture of my squared errors. So I'm back to my initial point. It's saying, well, if I want to minimize this problem, the only thing I have to do is mix my environments in the right proportions, and I'm going to satisfy this condition. And the worst part is that by changing the baseline, I can change the lambda E the way I want. Choosing the lambda 0, choosing the baseline is the same problem. And so the robust approach mixing the environments with the correct proportions. So here is an example. I have 4 distributions, P1, P2, P3, P4. And the robust approach says, I'm going to be good on all of them. And therefore, I'm going to be good in all the convex hull of these distributions. And this is attained by minimizing a specific mixture. Now, the thing that's interesting is that there might be distributions that are outside of this convex hull. So with barycentric coordinates that are slightly negative, and that can be a legitimate distribution, but I have no guarantee on this. What I've done doesn't say anything about something that's outside. And why is it important? Now, take another example. Take a search engine. My example is wrong, but if you take a search engine, it's interesting very often to classify the queries in different categories, like the query is commercial in nature or navigational in nature. That's quite important. And suppose that I have a number of environments, which are the set of queries today, yesterday, the day before yesterday, the day before yesterday, and so on. And quickly, you're going to see there are actually 3 kinds of queries. You have the queries that remain constant. The frequency is the same over all this period. Some of them are growing. Like, for instance, when you come close to a particular event, come close to Christmas, queries about Christmas presents are growing. And some of them are decreasing. After Christmas, the queries about Christmas presents are decreasing or going away. And the growing and the decreasing ones, they're a very small subset of everything. So what I have is that if I take my triangle here and say this, these are my many queries that are the same, that don't change. These are the ones that are decreasing in popularity, the ones increasing in popularities. My 4 days, they form a very small set of points that are very close to this. And if I'm robust, I'm going to be performing well in that little domain here. But in fact, if I'm waiting, let's say, 1 month, I'm going to move away in that direction. So what you see here is an example where having a guarantee that works only in the convex hull of my environment is not really sufficient. I can do better, and I would like to do better. In fact, it's the problem of interpolation and extrapolation. And interpolating is something that we understand we can do quite well. Extrapolating is always a mystery. So if we go back to this idea of learning stable properties, and you find that in a number of old philosophical works, suppose that I'm going to come back to my problem of calling. And you have a set of pictures taken from the web. There is a selection bias, and pictures are where I see a person on the phone often represent the person calling. Now, also, suppose I also have little movies. And let's say the movies have the same selection bias. Because if I take my little movie, at some point in the movie, somebody close to a phone is giving a call, is placing a call. But if I take the frames of the movie, even though at some point the movie is going to show the person calling, there is going to be the before calling and the after calling, where I have a lot of frames where somebody was close to a phone but not calling, and close to a phone and not calling, but because the call is finished. And that's interesting, because it means that if I take images from these different sources, pictures taken from the web or frames taken from movies, they both have the selection bias, like the correlation between the proximity of a person and a phone and the event of calling is high, but they have it in different ways. It differs in strength. And if it differs in strength, it means that if a regression system has the choice between two kinds of things, like for instance, features that represent the shape of the person, the position of the hand, and features that represent the presence of objects merely, the regressions will be different. If I compute the regression on the first data or the second data, they're not going to rely on the same features in the same way, because in the first case, the proximity is a more reliable indicator of calling, while in the second case, it's a bit less reliable and I have to use a little bit of something else, even though using this is still very favorable in terms of accuracy. And that tells us our idea that we would like to learn phenomena that remain invariant across environments. We really want to learn a regression or a classifier that uses the features in the same way across environments. If one of them is wobbly because it has different strength with different environments, we're going to say this one is suspicious. So this idea is very related to the notion that we don't take all the data as a single distribution. We look at its heterogeneous structure and say that if some correlation is maybe highly predictive but changes in strength across environments, we see it with suspicion. So why is it interesting? So let's first say invariant regression, which is a strong requirement. Suppose that instead of minimizing the maximum error across environments, I'm searching for a function that belongs to the minimum for all environments. It's not clear that it exists. It's not so simple to find it. But what does it mean about mixture coefficient? And if you say that f star is a stationary point of my error for all environments, it's also a stationary point of any superposition of my probability for, okay? And that's true for all lambdas, positive or negative. If some lambdas are negative, this is still true. So the invariance property, in a sense, has this, it's stronger, because we want something that's way stronger and maybe hard to do, to achieve. But if we achieve it, we don't just generalize to the distributions that are in the convex hull of the ones I have, but to the biggest extent that we can reach with, let's say, negative barycentric coordinates, which is what I wanted to say here. Well, some trivial existent cases, like In the noiseless case, maybe it exists. If there is a function that works and classifies everything, it exists. And these trivial existence cases annoy me because I don't know how to deal with them very well. But I'm going to be interested by the cases where there is no single F star that belongs to the minimum or that minimizes the regression for all my environments. And I'm going to say, well, I'm going to play with the function family, but maybe I should go straight to the thing. I'm going to say that I want to find the representation, phi of x. And in this representation, I want the regression from phi of x to y to be invariant across environments. So the idea there is that if my problem is noisy enough, and I don't know very well how to deal with the noiseless problems, and that's an issue, but if it's noisy enough, the only way I can find the function that's going to minimize my regression for all the distribution, all the environments, is by first projecting my patterns into a certain representation that essentially eliminates the features that are unstable, the features that are spuriously correlated to what I want. And that gives the idea that we can use this criterion of invariance not to just learn, but to also guide the creation of features. And that's very different from backpropagation. When you do a neural network and you have a hidden state in a network, these hidden states are created in a way that permits the best possible prediction. Here we're not interested by the best possible prediction. We're interested by a prediction that remains invariant across environments. And that's something that's very, very, very important in science, for instance. Suppose that you're watching an apple from follow tree. What do you have? You just have an image or a little movie. This is what you see. And you could pay attention to a lot of things. You could pay attention to the color of the apple. Like observe that when the apple is falling, very often it's red because it's ripe. But it doesn't tell you something very important, let's say, to the trajectory of the falling apple. You could look at the size of the leaves, the size of the tree, the size of the trunk, the number of leaves on the stem of the apple. But in fact, if you look at the right variables, let's say the position and the speed, you observe that all your apples now obey exactly the same equation. And because you observe it on all the apples, you can say, oh, maybe it's going to work on all falling objects. Maybe you have found something more important. So there are cases where it's not going to work. Like you have a kite, it's not going to work that way. But for a number of falling objects, the same equations are going to work. So there is some value in finding exactly the same solution. In the sense that finding exactly the solution is a hint that this solution is actually more general. And it's also a hint that the data or the representation of the phenomenon in which you find this invariant solution is something important. Now, there's a lot of related work. The first one is that this idea of invariance is in fact related to causation, and something that's been known for a long time. There is a work by Nancy Cartwright showing theorems. These are people working in philosophy, actually, they're epistemologists. But it's easy to understand. In the causation framework, let's say, of the statisticians, what you want to do is not predict what the system is going to do, but predict what the system is going to do when you intervene on the system. Like, for instance, if you want to look at the efficiency of a drug, and you can make some tests and everything, but what you want to know is, if I give that drug to everybody, will the population be better? And this is not obvious. When you want to do this, there are actually two things you can use. You can use your knowledge of the intervention. So I'm going to give the drug to everybody. And the second one is you can use what you believe remains invariant after and before the intervention. Initially, you give the drug just to a little test of test people. And after, you give the drug to the whole population. And if the probability of getting better, given that you have the drug or not, and all other variables of interest is preserved, then you can use that. So you're looking for a property that's invariant. And in fact, all the things like do calculus or the ignorability assumption of Grubin, they're all tools to try to define the mechanics to model these kind of things that are invariant. For instance, you have a graph, you intervene on the graph of causation, and you can detect that some distributions are going to be invariant and some conditional distributions are not going to be invariant, and do some kind of calculus. Now, invariance is attractive for learning because reconstructing causal graphs from data has proven very difficult, while learning invariance seems to be easier. If you're able to learn something that's stable across time or across heterogeneous conditions, you actually do something that's as powerful as doing causal inference, because you get half of the data, and that you can use directly. And it seems to be an interesting alternative. So I mentioned the paper of Jonas Peters that was a big inspiration for this work. And in the paper of Jonas Peters, it considers causal graphs on which you intervene. This is what the little hammers show. And each causal graph under intervention describes a slightly different distribution because of the intervention. Now you get all these distributions. You have a variable of interest that, let's say, is y. And you're going to try to find an invariant regression for y. So in the case of Jonas, he assumes that all the variables are known, so the representation is just selecting which variables I'm going to regress from. And what he shows is that under a certain number of caveats that are mostly technical, if you find an invariant representation, you find a set of variables such that when you compute the regression from these variables to y, you get the same one, then you found the direct antecedents of y in the graph, which is a very nice result. Now, the limitation of this, of course, is that you have to assume that you know which are the important variables. I want to assume that just get a bunch of pixels, finding the important variables is a difficult part, and this is just about narrowing. It's just you assume here that you have a small subset of variables, and you know that the important ones are a subset of them, and you have just to refine. But finding what's important to measure to start with is difficult. So another related topic is adversarial domain adaptation, which is a kind of recent thing. And the goal is to learn a classifier that does not depend on the environment. And the idea is that you want to learn a classifier that's you're going to train on some distributions, you're going to work well on the other ones. And in the simplest thing, you have an adversarial terms that says that if you take some states from a hidden layer somewhere and try to classify and say from which environment the data comes from, you cannot anymore. So you're trying to find a classifier that has hidden representation from which you cannot recover the environment. And if you think about the paper of Toralba-Frost I mentioned early, the observation that given an image you can say from which dataset it comes is already a problem. So they're trying to alleviate this by saying, I'll take my image and I go to a set of features from which I cannot recognize the dataset anymore. And now you realize this is too strong, because it might be that different environments have different probability of yes-no answer. So if you say that these features do not allow you to recognize the environment, it means that the distribution of these features in all the environments is the same. If it were different, you could say from which environments it comes better than chance. And if they're the same, it means that the distribution of the class label you're going to predict is the same in all environments, which is a bit too strong. And there are some other variants, and basically the question is whether you force P of H, the hidden layer, to be invariant from the environment, of P of H and Y joint, of P of Y given H, of P of H given Y. What we do is weaker. We just want the regression to be the same. And finally, you have robust supervised learning, which is something that happens, let's say, maybe the most common, the most popular idea about this is the PGD approach to resist adversarial examples, where you say essentially that instead of minimizing on the distribution of the data, you're going to define a set of neighboring distributions and minimize the maximum of your error on all these distributions. And well, in contrast, we use multiple environments. We suppose it comes from the data. It's not defined a priori. And then we invoke invariance. How much time do I have? 15 minutes? OK, so I'm going to start with the linear case. So in the linear case, you have x. The representation function is a matrix. The regression is a vector. And in fact, the whole operation is linear, is a certain W. And you can see already that it's very overdetermined, because you could change S a little bit and balance something in the regression back and forth. And you also have lots of solutions that are not interesting. If I choose S equals 0, of course it's invariant. It's just not very good, meaning that I'm just eliminating all the features. And you can see that what matters is the null space of S, which is the information I'm censoring for my system. And another difficulty is that if what matters is the null space of S, and S has a certain null space, a small change of S can completely cancel the null space. In the vicinity of a singular matrix, there are just plenty of non-singular matrices. The null space is 0, or just the null vector. So it's not it's a finicky criterion to minimize. But if you do a little bit of linear algebra, you can characterize the solution. And you don't characterize in terms of S and V, but instead of the W, the whole set. And you can say that the whole W's that satisfy the invariance property, in fact, if W satisfies the invariance property, meaning that there is a S and a V, and the V is the same for all environments, only if this thing is true, which I'm going to describe later. And then you can reconstruct the S's. There are lots of them. And in the linear least square, this equation represents an ellipsoid. So essentially, for each environment, you have an ellipsoid in the weight space. They all cross 0, because 0 is a solution, not an interesting one. And the W's that have the invariance properties are those that are at the intersection of all these ellipsoids, which is sort of bad news, because the intersection of ellipsoids typically is not connected. So it's going to be a bit difficult to search. I'm going to skip on this about computing ranks and high-rank solutions, and maybe go straight into some. So one possible idea is to use this criterion as a regularizer. So you have all these ellipsoids, and you're going to say, in order to be close to the intersection of the ellipsoids, I can add a term to the cost that.
The question is, one S for each environment, or the environments share S?
They all share S.
Share.
Everything is shared.
Okay.
There is only one classifier at the end.
Yeah, okay.
So the question is, what information S is going to remove in order to make sure that after applying S, the linear regression is the same for all environments. So it's the only one S, only one V. And surprisingly, there is actually it's not every W that has this property. So I can regularize towards them. And since I have an ellipsoid per environment, I can measure the distance to the ellipsoid, which happens to be a 4th degree thing, which is not fun, but we know it. And one way to look at it is say I have S and V, and I can insert a dummy multiplier here, theta, that's 1. I'm going to say it's 1. But I can compute the derivative of my cost function with respect to theta, and it turns out that this is exactly what I want. So basically, what I'm saying here is that maybe you've heard of domain adaptation layers. You have a system, and you have various domains or environments, and you say, well, I'm going to train on everything, but for each environment, I'm going to use a little extra layer that I'm going to optimize for that domain. And you can see theta is the domain adaptation layer, a trivial one. And what I'm saying is that actually I don't need to adjust it. So I'm looking for a solution that's such that if I had a domain adaptation layer, I don't need to change it to model all my environments properly. And there is equivalence between the two approaches. And this way of looking is interesting because if this is nonlinear, I can still make the same kind of reasoning. I can still say, well, I'm inserting a frozen domain adaptation layer. Its identity doesn't change anything. But what my regularization term says is that when I go from looking at all my environments, none of them is calling for a change of theta. So I'm going to take an example. I call it colored MNIST. Digits with misleading colors. So we take MNIST, and we split it in two classes. The low digits, so 0 to 4, the high digits, 5 to 9. And I told you I need noise in my system because I'm going to use noise to constrain the representation. So I'm adding 25% label noise. So the highest classification rate I can use by using the shape of the digits is 75%. But then I'm going to add colors. I'm going to say that if my class Y is 0, my digit is going to be red with probability 1 minus E, green with probability E, meaning that if E is small, my low digits are going to tend to be red, and high digits are going to tend to be green. And my two environments are going to be defined by specifying E between 0.1 and 0.2. And that means that if I use only the color, I'm going to classify better than if I use the shape. If I use the shape, I can be only 25% color, correct. If I use the color, in one environment, I can just have 10% error. In the other environment, I can have 20% error, both of which are less than 25% error, which is the best I can achieve because of my label noise. So I'm training with E equals 0.1, 0.2. And if I train with normal training, minimize the empirical risk, well, I get about something halfway between 10% and 20% error, which is normal. But if I test with E equals 0.9, I reverse the score scheme. Well, it doesn't work at all. If I do the same training but add the invariant regularization terms, and they're very painful to train. No, it's not nice numerics. It's painful. It's slowish and everything. But what I get is consistent performance. So basically, I was able to say that because the relation between my pattern and the color is not stable, I don't want to use it and have to rely on the shape, which is drowned in noise in that case, which doesn't make it very easy. And if you look at the output of my classifier, so these are dots corresponding to example in each of the environments. And you see that for the 0.1, 0.2, you get an answer like this. But for the green one, you get the opposite answer because it relies on the color, and the color has been switched. While if I train with this mixture, well, it's more reasonable, even though I have a little bit of crap that remains. So it's a small example, and it works only when it's very noisy, which is a problem. And the question next is to scale these kind of ideas up. And this is where we're starting having problems. First of all, we have numerical issues. The regularization term is very non-convex. It's normal. It's targeting the intersection of plenty of ellipsoids. And the discrete points that are all over the place, they're not connected. It's not going to be easy. And then there is something different about realizable problems. Because many of the problems that are interesting for people nowadays are problems where you can achieve zero errors, essentially. And I don't have this noise that allows me to make the system work. So I have to find a way. And in fact, if I go back to this realizable case, which is the case where, well, you know, there is a function that's going to represent everything. Let's look at my little observers here. I have a phenomenon, I have a scene, and I have a variable of interest that exists in the scene. Maybe it's not observable directly, that I call Y pre-labeling. And I get some kind of image X, and I get a bunch of people that I call labelers. This is what we do in supervised learning. And they're giving me labels that are Y post. Suppose the label is whether a person is calling, for instance. Turns out that the Y post, the labels that the labelers give, is not necessarily the truth, because somebody could be calling in hiding and you don't see calling, the person calling really. The labelers are going to say no, and they're going to agree. But in fact, the person was calling. So there is a slight difference between this, the why that's in reality and the why that comes from the labelers. Now, the labeling process is often designed to be as deterministic as possible. We train the labelers to be consistent. We ask questions in a way where there are not many ways to give answers. So we're trying to make sure that there is a function that belongs to all the environments. And that's true for the post-label. It's not necessarily true for the pre-label. Okay. So what this means is that in that setup, when you have a supervised problem where the labels are given by labelers, we artificially created the solution, the situation in which there is an invariance. Not because we found an invariance in the reality, but because the action of the labelers was invariant. And because there is no noise, I don't know how to sort them out. So that's my problem at the moment. So if I should conclude in this talk, I say that the statistical problem is only a proxy. That's something very important. And between the real problem and the statistical problem and the proxy, there is a huge gap that we haven't explored. And this initial idea that maybe you can program computer in a different way by teaching them to do things instead of programming them is not going to be achieved unless we understand what is in the gap between what we want to do and the statistical proxy. The second one is that nature doesn't shuffle these examples. We shuffle the example because it matches our ideas about learning, but by doing so, we're removing a lot of useful information. That one of this information is about the properties that are stable. And when you start looking at properties that are stable, invariant across environments, you start making sense of extrapolation. The idea that you can extrapolate to new environments. It sort of makes sense in that situation because when you're optimal for each of your environments, you're also optimal for mixture, possibly with negative barycentric coordinates, so you can go out of the strict interpolation. That invariance across environments is related to causation. It's an alternative view of causation. That's what I explained, that there are actually formal proofs that invariance is similar to causation. That you can try to find invariant representations to enable invariance. And that only works if it happens that not all representations enable invariance. If you have no noise, well, everything is invariant, so it doesn't work that easily. And this is why I have my problem at the end, that I want to understand how to slightly change this concept to make them applicable to the realizable problems, the one where you have zero error, which is tricky in different ways. That's it. Thank you.
Let's have 5 minutes for questions. Yes.
Thanks for the talk. Do we have a mic for the recording?
Do we have a mic for the questions?
I can repeat the question.
You can just.
One thing was there's lately, like in image classification, there's lately this work on learning policies to come up with good data augmentations. Basically, find policies that sort of put like squares or bend rotations on the images, basically break invariances or correlations, or basically break correlations that otherwise the neural network would overcome. Do you think this is like something to explore further?
Okay. So the question is about what I think about policies that try to determine which form of data augmentation works best. First of all, well, that could work, but it's not what I'm looking for. And the reason is that when you're speaking of data augmentation, you're in the situation where you define a ball around the distribution that you have. So you say, instead of taking examples, the examples I have, I change a little bit the examples and I create a combined distribution. So data augmentation is just a way to look in a slight ball around your distribution. This slight ball is arbitrary because you augment data in ways that you think are good. Like for instance, you're thinking, maybe I want to have more rotation, more translation, more jitter, more color changes. But what about the thing you didn't think of? Like for instance, turns out that all the pictures of a potato were taken with the same focal length and the same kind of camera, and that's detectable in the noise. But you didn't think of that one. If you didn't think of that one, you're not going to be able to fix it. So somehow, we want to be able to handle these kind of situations. And for this, we need extra information, and the extra information, I think, can be found in the heterogeneity of the distributions. Yes? Yeah, sorry.
Thanks for the great talk. So I was wondering how you can relate this non-shuffling idea with HGD, because we know that for HGD to work, we need, it works because it adds some noise. And if you think we shouldn't shuffle, then how will that affect training with HGD?
So the question is the connection between looking at data as non-heterogeneous versus SGD, because the SGD theory is very often connected on RID. Well, this is why we looked at it as saying we have a set of sub-distributions, and we assume we had training data from each of them, and so we can do SGD on each of them, or we can try to have a regularizer on top of it. But it's true that in many situations, the formulations you can give to a problem like this are challenging SGD. That's true. It's difficult to find the SGD solution that computes the right solution. And you have people who do it with adversarial means. And adversarial is very hot and interesting, but you have to realize that it's awfully slow. Just training a GAN is terrible compared to training a network. I couldn't show you a 30-year-old demo of training a substantial GAN because that was totally out of reach. I can show SGD with a CNN and image recognition, no problem. So the adversarial way is slowish, and having constraints of the distribution, saying that the distribution of hidden layer and Y satisfies certain relations, is always difficult to express with SGD. But that's normal, because we are going away from having a criterion that's a simple average on my data. And SGD optimizes an average on the data. Yeah, that's a problem.
I have the mic, so.
Yeah?
So, great talk. Like, I love the paper. For me, intuitively, it makes a lot of sense when you're doing classification. You want to find the invariant relationship. It's kind of like spot the difference. Hey, there's always a cow in all these photos. But suppose I'm trying to do an inference task, and I use your IRM predictor, and it's also like the expected outcome of Y condition on, treatment and covariates. What is the invariant relationship in that sense, when we're thinking about, causal inference?
If you take causal inference, let's say with graph in the Perlian way, and you take the typical situations of confounding, non-confounding, if you just collect conditional distributions on the basis of what you observe without taking account, without conditioning over the potentially confounding variables, this conditional you obtain is not invariant when you apply the intervention. On the other hand, if you condition with respect to all the potential confounders, the distributions you obtain is then invariant.
So IRM would just not work if there's any if there's any unobserved confounding that you're not account for.
Well, first of all, IRM doesn't. It's not an end; it's a beginning.
Okay.
So it doesn't do much. No, we were happy to do the color amnist, and we have a hard time making it bigger or something like this. But what's interesting is that it's an interesting direction where you try to go away from the statistical problem and look for other properties of the solution that you believe should be important. In the situation we consider, we assume that we have, let's say, rich data, like images, and by censoring information, you can reduce it to a set of variables that's sufficient to make a reasonable prediction that's invariant. Now you have the situation where you have hidden variables, let's say In the case of causation, there would be confounders that you don't see. Well, then you have a serious problem, because either you reconstruct the confounders, or you just say there is a confounder that I don't see, so I cannot conclude. And the mechanics of, let's say, do calculus is going to tell you that be careful, there is something bizarre, but you have to put it in assumptions, essentially. It's just going to tell you, I cannot compute this do probability on the basis of what you have now. You need to make a different experiment. And it's not exactly the situation I consider where I have very rich data to start with, large images, where maybe somewhere in the image I have everything I want to measure. But it's true that in physics, for instance, sometimes you cannot predict what's happening because of things you can't see. And the history of mankind has been to find ways to see them. So yeah. So no, I can't do that, and I don't know how to do it, and I don't know if anybody can, but it seems that as a group of people, the scientific process has been able to do it in many interesting cases.
Thank you.
Hi, thank you for your talk. I was just wondering how the extrapolation system works exactly, because so in the MNIST example, we have green and red digits, but what if you want to be invariant to color entirely and have images that are, say, purple, for example? Like even in the related work, for example, the domain adversarial approach trains on a loss that knows that this is coming from this domain, and so like there's a predefined set of domains. So how does it generalize to?
So in the case of this experiment, the thing that's interesting is that it doesn't not only generalize to color schemes that are in the same range as the one I used for training, it generalized to the completely opposite color scheme, which means that essentially the system became colorblind.
Okay.
And even though it had two data sets that were both biased, but the fact that they were biased in slightly different ways was used to say that we don't want to use color at all. So if you introduce a new color, it's still going to work. So that's the good point. The bad point is that, first of all, it's not a very efficient process. When you have data sets that are very, very little in terms of the dependence between color and label, it takes a while to see it. And that we obviously, humans, do it in a much easier way, which I can't describe. I wish I could, but I can't.
All right, thank you.
Okay, let's thank the speaker again. Thank for you to help you remember us for the future.
I've been with this.
So I can carry it for you until the end of the day. If we can make a photo, we always do a photo with a black. I think we're going to just cut it. Yeah, there we go. Okay, let's do it now.